Hello, everybody. I'm Jeffrey, and this is my colleague, Kurt. We are from Amplitude Analytics. We'll get a little more into that later. What we're going to talk about today is kind of our process of scaling our data ingestion pipeline and how we migrate a bunch of metadata stores from SQL to DynamoDB. You guys all heard a lot about DynamoDB so far, and we're excited to share some of our experiences with it as well.
I'm Kurt, studied CS at University of Arizona. Previously worked at Amazon and Marketplace and on the Kinesis team. And started working at Amplitude a year ago, focusing on the data ingestion pipeline.
And I'm Jeffrey. I graduated from Stanford in 2010, studying computer science as well. Previously worked on distributed systems at Palantir and Sumo Logic over the last few years. 2 years ago, I started at Amplitude, originally as a VP of engineering, moving into the chief architect role recently to focus on the technical vision of the company. We were founded in 2012 by Spencer and Curtis. They went through YC, and basically we are an event-based mobile and web analytics platform for understanding user behavior. So you can think of something like the next generation of Google Analytics or Flurry or things like that. We raised a Series A from Benchmark in 2015, and actually we're happy to announce that this morning we just disclosed our Series B from Battery. So it's been a busy day at the office. To give you a little bit of context, I want to share what we do first so you have something to think about as we go into all the technology. There's kind of two parts of our architecture, I guess. One is the event collection side. So when our customers use us, they'll when they're building a mobile app or a website, they'll instrument our SDK into their code, and then they'll basically track different events that users perform within their application, and we collect all that data and provide behavioral analytics on it. I find it useful to provide an example of what this actually means. This is one of our more innovative products called Compass, and what it does is, given the actions that a user performs in your app, let's say you're Facebook or something, and you have actions that are like adding a friend or sharing a status update or uploading a photo. It basically looks through all the data and finds correlations between those actions and whether users are retained within your application long term. So this is really helpful for kind of guiding the product direction of an application and figuring out what behaviors correlate strongly with users coming back and becoming power users of your application. In this presentation, as I mentioned at the beginning, we're going to talk about our data ingestion pipeline. So this is like how the data gets to us and what we do with the data before it kind of becomes a process within our system. So here's a very high level square diagram of all of the ingestion pipeline in our system. So obviously it starts with the data collection servers. It's just a standard web endpoint. Everything is immediately dropped into a Kafka cluster. For those of you who are not familiar, Kafka is very popular queuing technologies these days for very high volume log data, and event data is very similar to log data, and so we use it quite heavily. So we drop it in Kafka cluster immediately for durability, so that we can immediately tell the client that we've accepted it. And then it goes through a data transformation process, which we'll get into later. After that, it gets dropped into a second Kafka cluster where it then basically forks to a bunch of downstream data processing things. So what we're going to be focusing on today is the data transformation process. And so we'll be talking about all of the pre-processing we do on the data before it kind of gets handled by the rest of the system. What does this data transformation pipeline actually do? At the very basic level, it takes HTTP requests containing the raw data. These come from our SDKs that are in mobile apps or websites, and transforms them into proper events that the rest of the system can understand. And so what does this actually look like? Here's kind of a simple example. The HTTP request might contain the API key of the application to tell us which one it is, and then some information like the user, the device, the timestamp, like what type of event is being performed. In this case, play song for, say, a music application, and then some user properties potentially associated with the person. And the transformation process, it doesn't look too different at the end, but it adds a few pieces of important information. So app is what we resolve the API key to. You'll notice a field called Amplitude ID, which we'll talk a lot more about later, but that's kind of our internal resolution of who the user is. And then you'll see potentially other user properties appearing based on historical data. We'll get into that as well as a few other things. And so the concept of this transformation is relatively simple, but the important thing is that it has to operate at scale. Today we process at the high times or peak times during the day about 40,000 events per second. And so, and that's growing very quickly. And so we're constantly thinking about how to make sure this transformation process is scalable. Here's kind of the key steps of the data transform pipeline. I'll just talk about them very briefly before we get into the ones that are most relevant to this discussion. First is request validation, kind of simple stuff. We decide whether it's a good thing or whether it's a good request or not. Sometimes we get spammed by people that just send bad data. Timestamp adjustment. As it turns out, mobile phones are often not they don't have like MTP on them and everything, so they're not recording the right timestamp. And when the data comes in, we don't want timestamps to be all messed up, and so we kind of resolve the client and server time differential. Deduplication. Mobile devices also have poor connections typically, and so they might send a request and then they don't really know if they got a response, and so the client will obviously retry that so the data isn't lost. And then on the server side, we need to understand that data might have come in before and deduplicate it. And then we also do a bunch of integrations. We are primarily an analytics service, but people like to hook up a lot of different things to analytics services. This includes like marketing tools if you want to send push notifications, or attribution tools if you want to track like your marketing channels and figure out where you're coming from. So we'll do all that work in the transformation pipeline. And the last two, which are really the ones that we're going to focus on and see how DynamoDB helps us, are applying user properties and resolving Amplitude ID. Yeah, as we saw previously, the user properties that came in on the event were like age equals 30. I apologize, I should have put this here again. But a new property called like gender female appeared. And so what is this, like why did that happen? And so in our system, user properties are associated with the user. At some point in time, we are informed that the user's gender is female or their age is 30. And all future events get those properties applied to them. And so this is like a fully denormalized thing where the user is not really separate from the event. The properties are all applied on the event to make it easier to query later. And so in the SQL world, we had a user properties table where it's very simple. It's got the app, it's got the Amplitude ID, which is our internal resolution of who the user is, and then we're using an HStore column in Postgres, which is just key value mapping. And so when we get new user properties, we update them, and then when we get new events, we apply the existing user properties to the event, and it's kind of as simple as that. And so yeah, the context around kind of all the two steps of the pipeline I'm going to discuss is we used to do everything in SQL. This was like a year and a half back, and then we'll see why and how we switched to Dynamo. So the introduction to all this is going to be in SQL. So resolving Amplitude ID is a somewhat more complicated process. I'll go through a little bit about what actually happens there. So a user ID is the customer-defined identifier of who the user is. So this could be like an email or a login, or if you have an internal ID in your database, people will often use that as the user ID in our system. And that's kind of like the first order thing that tells us who the user is. If the customer says the user is this person, then we will just always assume that that's true and not try to do anything fancy. Device ID is often used as well, which is usually a random token generated on the mobile device or in the browser to indicate that all the events coming from a certain session or a computer or phone are the same. And so when you don't have a user ID, let's say someone just opens your app or your website and they haven't logged in, you don't know who they are, they'll just have a device ID that ties all of their events coming from that device together. And so lastly, we had these two pieces of information from the SDK, and then our job is to determine the Amplitude ID, which is to say like which canonical user within our system this is, and figure out when two users are the same. User ID tells you for sure that this is a user, and so the interesting case is when you don't have a user ID. So let's say you have a device ID, someone's anonymously sending you events, and then so when the event comes in, you have to assign them an Amplitude ID. They have some canonical ID within the system, and that's who they are. What becomes where it becomes a little bit more interesting is later when they log in. Now you have a user ID and device ID, and so you want to make sure that when the user log in, they assume the Amplitude ID of that device ID. And then potentially they can log in on a different system, and you want to make sure that the Amplitude IDs there are resolved as well. When we're resolving Amplitude ID, there's two tables, user IDs and device IDs. I'll talk about both of them. So again, these tables are fairly simple. It's got the app, which is the context in which it's running, the device ID, the Amplitude ID resolved to, and then a timestamp. This is because on a single device, you can have potentially multiple different users, right? Especially true with like browsers. It's often the case that let's say you're in like a library or something, and lots of people are using the same browser. So the access patterns for this are when when you see an anonymous event comes in, you need to know whether there's already been an Amplitude ID assigned to that. And so that's when you use the app device ID index. It's also got time at the end, which I'll get into a little bit later. But that just looks up, is there an Amplitude ID that we've already assigned to this device anonymously? If so, this new anonymous user, we should assume is the same as the previous one and use that Amplitude ID. When you look up a user within the system, sometimes you just want to see all the devices they're on, and to show that, you need that second index. The user IDs table. So again, when we see a user ID, that is the first thing that we use, and so this app user ID index is kind of a very, I don't know, like the first order index within the resolution process. If an entry exists for that user ID already, kind of the whole resolution process stops, and we're like, this is the Amplitude ID. There's no reason for us to continue trying to figure out if there's any weird device correlations between people. This is definitely that person. So that's pretty simple. And then the app Amplitude ID index is used for a somewhat complicated merge process where it can be the case that we actually have two Amplitude IDs that we need to merge together. Not going to go into too much detail about that specific use case, but it's important that we have the lookup by app Amplitude ID to identify that case. So now we've kind of established the two different use cases that we have and how they manifested in SQL.
Why SQL? A lot of people are usually familiar with it, and you don't really know like what your use cases, your business use cases are going to be. So it just gives you a lot of flexibility. You got ACID. You want to add more indexes, you can always do that, and they'll be strongly consistent. If you end up having complicated transactional use cases, you know that you'll be able to do those. Scaling is very difficult. Typically, like all of those things break down once you need to have multiple instances running. Why Dynamo? Simple API. It's a basic key value store. Once you understand your use cases, and you've identified that like sort of the limited ways that you want to access the data, you'll be able to make like a confident decision that Dynamo is right for you. Last thing, conditional updates, which sort of allow you to model a lot of the transactional concepts, but usually requiring some limitations on how exactly that all works. Final reason, it's really easy to manage and scale. You just go click buttons, you get more hosts, data gets spread around. Jeffrey talked about the user properties table. That's like a good example of like, you just have a table that you don't know what you're gonna do with it necessarily. But then after the sort of the use cases have stabilized, you realize that you really only have this one access pattern. You're looking it up by its primary key and merging old user properties with the current user properties on an event, or adding new user properties to sort of just a blob of data. So you basically just have like a dictionary as the value under some primary key. Here's an example. You can sort of see this sort of properties that people have.
This was mentioned in the previous talk as well, but we do cache our Dynamo reads pretty heavily. As with any database, caching is kind of a natural way to reduce the load on the more contentious resource, which is typically I/O, or in Dynamo's case, the capacity. We use Redis a lot because the key value data model in Redis maps to Dynamo pretty nicely. It's easy. We have about 80% hit rate on our cache right now, and just reduces costs and is really nice. Amplitude ID resolution use case in Dynamo, which is somewhat more complicated because we have multiple lookups on these tables, as you saw from the multiple indexes on the SQL tables before. One important thing to note is that the items are immutable, so we don't do updates, but we do inserts and we do reads. Based on our SQL schema before, these were the fields and these were the lookups that we did on the table. So how do we turn that into a Dynamo schema? Hopefully from your previous talk, you have now the tools to figure that out. But here's what we figured out. One thing to note is that the hash key. So although the main lookup is app plus device ID plus time, the hash key we do use as app plus device ID because sometimes we do want to look up all of the Amplitude IDs on a device ID, and so then we use time as the range key. And so this is this fits kind of within the schema design pattern of Dynamo because app device ID is quite a large key space. A device ID is like associated with a specific phone or browser, and so there are a lot of them, and so we don't have too much locality there. And for the second lookup, the Amplitude ID direction to figure out all the devices that this user is on. We're okay with this being eventually consistent because this reverse lookup is not part of the transformation process itself, but rather like in our interface, someone can go look up all the device IDs for an Amplitude ID. And so it's not like critical that we have the mapping perfect at all points in time. As long as it eventually shows up, we're okay with that. So this table ends up fitting the Dynamo schema pretty well, and it helps that it doesn't have too many different fields, or rather, it doesn't have too many different access patterns, and so it transitions much more nicely to Dynamo. The user IDs table, a little bit more complicated because the two lookups are both need to be strongly consistent. They are both resolved in the transformation process, and so we have to figure out how to get at least emulate strong consistency on both of them. We kind of use the hash key, standard app and user ID. Again, that's a relatively large key space because that corresponds to like a single user, an end user of ours, rather than one of our customers. And we have a global secondary index, again, with app Amplitude ID. But as I mentioned, this needs to be strongly consistent during the resolution process. And so how do we get around that? The GSIs don't support strong consistency, which makes sense because that's a very difficult distributed systems problem, actually. And so we do several mitigation factors as well as just some reasoning about our use case to get around this. So we write things to cache immediately when we insert them into the table. And so that by itself kind of eliminates the vast majority of problems, right? As long as your caches are up, the eventual consistency will certainly take effect before they flush or things like that. It's possible, however, that the in-memory cache, you restart it, or the Redis cache, it crashes. Who knows? In that case, we still don't want too many problems. Fortunately, we can reason pretty nicely about this in that the actual amp or app plus Amplitude ID lookup only happens on a specific kind of a specific situation where two users are like logging onto the same device at the same time. So it's actually just this really rare thing where it's very unlikely that you're going to have like a phone and have two people log into the app at the same time. And so because of that, it's actually like not a case that we care that much about. And so between the relative rarity of the use case as well as the in-memory caching plus Redis caching, we kind of assume that this is a good enough approximation of the strong consistency. We can identify these cases pretty easily, and we haven't run into any issues, so we're pretty happy with how that worked out. And so, despite not having the strong consistency of a SQL index, we were able to solve this use case relatively straightforward in Dynamo. One thing that's kind of interesting, especially if you're running SQL now, is how to migrate from SQL to DynamoDB. We have, I guess, multiple terabytes is only the case now. Previously, we have maybe hundreds of gigabytes in our SQL database, and we can't really just stop everything, let it run a big migration that probably takes a few hours, if not like maybe even a day, depending on what kind of capacity you're provisioning. And so we need to figure out how to get over to DynamoDB without incurring any downtime or anything like that. Originally, you're reading and writing to SQL, and there's nothing happening with Dynamo. So the first step is to start writing to Dynamo. So we're fortunate that there are no updates, but even if you have updates, you can just write updated items to Dynamo. As long as you always read from Dynamo first and then SQL, you kind of always have the latest thing. There are a few edge cases where we do need some sort of transactionality, but across the two databases, but that's not a big deal. We use some locks in that case. So now you're writing all the new items to Dynamo, and so at some point you probably want to shut down the SQL database. So you're not running it forever. You don't have to maintain all that legacy code that's talking to the SQL database, and so we add like a background migration process that kind of slowly reads through all the SQL data and inserts it into Dynamo, and eventually you end up with everything in Dynamo, and then you can shut down your SQL database and be happy. Kind of end on a few DynamoDB best practices and some stuff that we've learned might be useful to y'all if you start using it. Capacity can be expensive at DynamoDB depending on your workload. So taking advantage of utilization patterns is nice. Here's the utilization, I think the read utilization of one of our tables. Obviously it's pretty cyclic with a daily cycle. And there's this nice tool called Dynamic DynamoDB, which kind of monitors your capacity usage and kind of adjusts your capacity for you, so you don't have to do it yourself. Unfortunately, this picture is not great because I didn't have time to pull up a good screenshot. But usually, it'll look like the capacity is like roughly following your utilization. Hotspots are definitely your enemy. One bad key can affect that partition and cause like everything that's writing or reading from that partition to slow down and cause a bunch of basically propagate a lot of issues throughout the rest of your system. So even though we thought pretty carefully about the key distribution in our schema design, it's difficult to completely prevent hotspots. So sometimes users will just the end users of our customers' applications will suddenly do a bunch of stuff, or often our customers will instrument like some programmatic things that will fire let's say 10,000 events for a user instantly, and in that case, or testing exactly. That will often cause a hotspot to kind of manifest. With the burst capacity, it's not too often, but if enough of these things happen at once, you randomly can get a partition overloaded. And so what we do is we actually monitor the throttling on our database. So DynamoDB will report throttling metrics when you've exceeded the allowed rate on a partition. And so when we do that, so that lower red line is kind of like where our capacity normally is at. You'll notice that it's already quite a bit higher than our consumed capacity because of this kind of natural hotspot stuff that happens. But when it gets really bad, we actually monitor the throttling. There's supposedly a separate graph here that shows you throttling, but it didn't actually show up. We see the throttling's happening, and so we don't want the whole system to kind of grind to a halt. That would be like definitely the worst thing to happen, and so we just temporarily bump up the capacity, kind of absorb that load. It's kind of an extension of the burst thing, if you will. So we pay a little bit more cost during that time in order to prevent the system from slowing down. And then once we've seen that it goes away, we kind of bring it back down and let it keep going. And so we've kind of built that simple throttling or simple monitoring mechanism for throttling ourselves, and it's worked out pretty well. It reduces a lot of random incidents that pop up that don't really have anything actionable except to increase the capacity of your Dynamo table. Recap really quick, all the stuff we went over. So we originally stored all this metadata related to the event transformation process. As we scaled beyond the throughput of a single process box, we eventually migrated them to Dynamo. Dynamo is, again, we want to really emphasize this point. The reason we use it is that it's easy to use and scale. It's not necessarily the cheapest thing, but it's pretty reasonable in price. It's not necessarily the most flexible thing, but if your use case fits it, it's really easy to use and scale. And all the complexity of a database like this is very much hidden behind the scenes. Whereas let's say you were trying to run something like Cassandra yourself, that's certainly going to be more complicated than the Dynamo API. We were able to work around the lack of full relational DB support. It's not always trivial depending on your use case. So in our user properties case, it's a very natural mapping to Dynamo, and so it works out. In our device IDs and user IDs case, they're a little bit less obvious, but you can kind of fit them. So like all of these things you get from a full relational database, while they're useful at the beginning when you're kind of prioritizing flexibility and the ability to do different things that you didn't anticipate. Once you have a use case that you understand and you need to scale, Dynamo actually works really well. And lastly, managing capacity is important in Dynamo in order to keep throughput high and costs low. As I said, monitoring is really useful to make sure that you're not slowing down unnecessarily and to keep your costs in check.